So I have two more really closely related definitions here that we'll use to wrap up this section. What we're defining here is the degree of a vertex. Right? The degree of a vertex is just the number of edges that are incident on V with a loop counted twice. All right, so I've got a graph here for us to look at, right? And this is actually pretty straightforward. If we look at V1, there are two edges, this one here and this one here, that are incident on V1. So I would say the degree of V1 is 2. All right, then if you look down here, V4, there are 1, 2, 3 edges that are incident on V4. So I would say that the degree of V4 is 3. If we kind of continue working our way around here, the degree of V3 is 2. There are 2 edges incident to it. And finally, over here, the degree of V2 is going to be 3. All right, and the last part here, the total degree of a graph is just the sum of all the individual degrees of its vertices. So I would say the degree of G is 2, 4, and 6. The degree of G is going to be 10. So in a sense, this gives us kind of a way to measure the size of a graph, right? How many connections there are within one. So I've got a theorem for us here to talk about. It's going to be our first graph theory theorem. And the proof is pretty straightforward, right? Which makes it a nice place to start. It's actually got a nice little name, right? It's called the handshake theorem. So what this says is that if G is a graph, then the sum of the degrees of all the vertices, that is the total degree of the graph, is equal to twice the number of edges. All right, well, let's see how this works. So let me put some points here for us to kind of illustrate what's going on. And before I add anything, I want to have just kind of this edgeless graph. Note the degree is 0. Right, so at this point, the degree is 0. Now, what happens when we start adding edges? Right, well, every time I add an edge, it connects 2 vertices. So the degree of that vertex went up by 1, and the degree of this vertex went up by 1, which means the total degree of the graph went up by 2. Right, suppose I add another one. Well, the same thing is going to keep happening. Every time I add an edge, the total degree of the graph goes up by 2, and this includes if I add a loop. Right? Because if we add a loop, something that's incident to itself, we add 1 for each of the connections. So even with loops, this goes up by 2. Right? One thing I want you to notice here, right? How many 2's did I add? Well, I added 1 for each edge. So this is equal to the number. This isn't equal to. We have the number of edges in 2's in the sum. And this does have to be finite. It does have to stop, because our graphs do have to have a finite number of vertices and a finite number of edges. That was back in the definition. All right, so now look, I'm going to kind of do the obvious thing here. I'm going to factor out a 2. And all that's left is this string of 1's. Well, how many 1's are there? Well, remember, there's 1 for each edge. Right, so 1 plus 1 plus 1, if I add all of these up, this is 2 times the number of edges, which is exactly what I wanted to show. Right, that was my theorem. I've got a quick corollary here for us. Remember, corollaries are kind of short little proofs that follow immediately from something else that we just did. And this corollary says the degree of a graph has to be even. Right, well, we saw in the last proof that the degree of a graph is equal to 2 times the size of its edge set. Well, this is an integer, and so the degree is 2 times some integer, which is our definition of an even number. So the degree of a graph has to be even. All right, so that brings us to the end of the first section here. In the next section, we're going to start talking about different ways that we can move around a graph, different ways that we can get from one vertex to another, and some of the consequences of those definitions.